In response to my last video, Sam Robbins asked, so how would I apply the knowledge of a peak at 40 Hertz to settings I'd change in beta flight to improve flight? And that's actually a pretty deep question. We're getting into the realm of signals analysis or spectrum analysis, which is a topic that people devote their whole careers to, and I'm not one of those people. But I can tell you a few things in keeping with my overall philosophy of helping to educate people who know even less about a topic than me, while still hopefully providing accurate and useful information. So if we look at a spectrogram here, I guess actually this is not a spectrogram, it's an FFT trace, fast Fourier transform, and what it is showing us is the magnitude of signal energy at various frequencies. So when we see a peak in the spectrum, I keep calling it a spectrogram because I've been working with them so much lately. When we see a peak in the graph here, for example, at 200 Hertz, that's telling us that there is a lot of energy at that frequency. On the other hand, when we see very little energy up here, that's telling us there's very little frequency or very little energy at those frequencies. One of the things you're going to notice when you look at these graphs is that some of them go to 500 Hertz and some of them go to 250, and some of them go to other numbers. And that's because of a thing called the Nyquist Shannon sampling theorem, which is it's commonly shortened to just the Nyquist theorem. Sorry, Shannon. And it says that in order to accurately record and reconstruct a signal, you have to sample the signal at twice its frequency. So if I had a 250 Hertz sine wave, I would need to sample it at 500 Hertz in order to reconstruct it on the other end. And when you have a signal like this one that's made up of many different frequencies, you need to sample it at twice the highest frequency that you are trying to record. And the reason we see different frequencies here is because of the loop time of the copter. The sampling frequency for black box is related to the loop time. It samples once per loop or once per every other loop or what have you. So in this case, the fact that we see 250 as the highest frequency here means that we were sampling at 500 Hertz or a loop time of 2000 microseconds. On the other hand, if we look at these graphs with a top frequency of 500, it means we were sampling at 1 kilohertz or a loop time of 1000. Okay, so that's why you see differences there and why sometimes they stop at 250 and other times they don't. Let's go back to, let's say this trace here. So then, how can we interpret this? Well, the first thing I want to show you is that down here at the bottom of the graph, say at below 20 or 25 Hertz, we've got this huge peak in signal energy, and that is your actual stick inputs and the wind blowing your copter around and so forth. That stuff is all happening in relatively low frequencies below 20, say 20 Hertz roughly. When maybe 50 Hertz, maybe there's some useful data as high as 50 Hertz, but less, as shown by the fact that there's less magnitude there. So that stuff, we're not going to worry about that. That's good. We want to keep that. And that's why if we start setting our gyro cut, we can see in this case, gyro LPF was 188 and gyro cut was 60. A gyro cut of 60 is going to mean that we are 3 dB down at 60 Hertz and then further reducing the signal energy or the signal strength when we get above that. But if our gyro cut is 60, it means that by the time we get down to 40 or 30, we're basically not reducing the signal energy at all. We're just not touching that much at all. So that stuff we can kind of ignore. What else can make these peaks? Well, one of the main things that can make these peaks in signal energy is harmonics. So a harmonic is if you have a signal, let's say it's at 500 Hertz, there are going to be peaks in signal energy at half that, a third that, and so on, going up and down the frequency band. And those harmonics are going to be weaker than the fundamental, but especially the second harmonic can still be quite strong. well, the second, the half, one half frequency. So I guess that's actually the first harmonic. So if we pull up the calculator, let's say we have a 2300 kV motor, and let's say we're running a 3S battery. Let's say it's at 11.4 volts. That's 26,000 RPMs. It's common to see an actual motor with a prop on it running at between, say, 70 and 80% of its free RPM. So let's multiply that by 0.75. And then that's RPMs. So to go from RPMs to hertz, we divide by 60, and we get 327 hertz. So the fundamental frequency for a hypothetical 3S copter running a 2300 kV motor with maybe a 6-inch prop or a 5-inch prop might be 327 hertz. And you could do that same math for 4S and get a slightly higher number. What we see though is that for the mini quads that a lot of people are flying and that are a lot of the focus of a lot of the effort of black box and clean flight and beta flight, the fundamental frequency of the props is maybe between around 350 and 400 hertz. And so what that means is that the first harmonic is going to be around 150 to 180 hertz. Now that's, of course, those numbers assume full throttle. Full throttle is going to get you max RPM. In reality, you're not running full throttle all the time, so your actual frequency is, your fundamental frequency is going to move around. And that's where those spectrograms that we generated with Octave come in handy, because they can show you how the fundamental frequency or the harmonic moves around as your throttle position changes, as various other things happen. This is just giving us a sort of overall big picture view of the whole thing. But we can see we've got this peak here, and that is probably the harmonic of the motor frequency. If we look at another one, likewise here, we've got a peak at 200. The fact that this drops off so sharply above 300 really stands out. We really should be seeing the motor's fundamental here. If we've got our harmonic peak at 200, we should really be seeing the fundamental at 400. There's probably some kind of filter that is just creaming this data. I don't know more about that though. That you have to rely on somebody who knows about the internal architecture of the MPU to really figure out what's going on there. But the fact that above 300 hertz, it just dies. Either I did something in generating the data, or black box did, or there's something going on with the filtering in the MPU to cause that. So I don't know why we don't see that, the fundamental there. But we've got a harmonic at 200, and then here at 100 we've got another peak, which is probably the next harmonic down. So the harmonics go by halves. So if our fundamental is at 400, we're going to have a harmonic at 200, and a harmonic at 100, and so on. So when we look at these graphs and we see these peaks, let me find another good graph. When we look at these graphs and we see peaks like this, that is probably a harmonic of the prop frequency, and there's probably nothing you can really do about that. But filtering, even with a gyro cut of 100, or maybe somewhere between 50 and 100, we should be able to reduce those to the point where they're not affecting us very much. If we were to zoom out, I've cut off this stuff here so we can pay attention to the harmonics. If we were to zoom out, we would see that the magnitude of the frequencies of interest, the actual stick inputs and so on, is way higher than this harmonic. This is exaggerated because I've zoomed in specifically to exaggerate it. So the actual signal to noise ratio between this first harmonic and the actual inputs we really care about is pretty good, and we're not too worried about that. So then we get down into this middling band where between, say, 50 and 100, 40, 30, and 100, where we might start to see other peaks. So one thing that could be is a harmonic. And the other thing it could be, especially if it's down, say, in the 20 or 30 range, the other thing it could be is aliasing. I'm looking for another example. Yeah, we'll pick this one. So aliasing occurs anytime you undersample. So if I've got a signal and it's going at 1 kilohertz, and I'm only sampling at 500 hertz, aliasing can occur. And what aliasing does is it takes frequencies that exist at a higher frequency and it folds them down into the lower frequencies. If you want to know more about aliasing, you can start researching it, and it's a scholarly topic that you can read a lot about. But the point is that anytime you're undersampling, you are potentially going to create phantom peaks in your frequency data that aren't really there in terms of the copter is not really moving, but it will look to the PID controller as if there was movement that wasn't really there. So what do you do when you see these peaks down in this range? When you see peaks up above 100 hertz, you know it's probably not really worth worrying about, because you're probably filtering the heck out of that with your gyro LPF and your gyro cut. If you're running gyro LPF 188 and gyro cut of 0, maybe some of this harmonic is going to start getting in there, right? Maybe. But if you're running gyro LPF 188, gyro cut 100, this stuff is all just getting knocked down to nothingness relative to the magnitude of the actual signal. But when you start seeing these peaks down here, chances are really good that that's not a harmonic. And if it is a harmonic, what are you going to do? Are you going to change your props? I mean, if you have a severely out of balance motor or severely out of balance prop, you could get the point where one of these harmonics is down in this area, this area here, and it's actually big enough to matter. But probably you're not in that situation. Probably most people they don't have that much vibration overall. So the other thing that could be causing it is aliasing, and the way to get rid of that is to not undersample. So the best case scenario for most people is going to be to run gyro LPF equals 188, which forces the gyro sampling rate to 1 kilohertz, and then run a loop time of 1000, which means that you are not undersampling at all. And that's going to get rid of any aliasing related noise. If you can't run loop time 1000 for whatever reason, go ahead and run loop time 2000, and that's the best case is no aliasing at all, but the second best case is 2 to 1. That's the least amount of aliasing next to 1 to 1. Those two scenarios are going to do everything that's really possible to get rid of any aliasing related peaks in your spectrum. At that point, if you still have peaks, then you may want to start looking at filtering. And you may want to start, like in this case, if we were sure that this wasn't aliasing, and we were sure that it was like a real thing that was really there, first of all, we would want to examine anything mechanical we could do to the copter to get rid of that peak. If you had a loose nut or something, loose nut holding your flight controller down, or you'd sheared a bolt maybe or a standoff, and it was rattling a little bit, that would create potentially some resonance or some noise here that would create a peak that you could get rid of by tightening down your bolts. But if you're really sure that you've dealt with aliasing and you're sure that there's nothing loose, then the only thing to do is to start filtering and to pick your cutoff frequency to try to filter this stuff out. And again, we see a peak here because I've zoomed in to try and really focus on it. But the actual magnitude of the peak, it's at something like 1 to 2. It's in that range, 1.14 to 2.29. This data here is off the chart at 10 or 15. Realistically, just don't even care about that. The signal noise ratio is so high, it probably doesn't matter at all. And that brings me to the final thing that I always want to reiterate. It's easy to get caught up in these graphs and just spend all day digging into them. Well, if you're like me, it is. But at the end of the day, the only thing that matters is how the copter flies. Don't get so caught up in this stuff that you try and sort of refine it to a point where if it flies good, who cares, right? So if you're having problems, then start looking at these graphs, and if you start seeing weird stuff, like, maybe you got a whole bunch of peaks here, like what is that? I don't know. Or here's an extra peak here, right? Maybe that's worth digging into. But if it flies good, just leave it alone. Last thing before I run out of time. This, I think, is what I would ideally like to see. A peak at the harmonic, and then a nice, quiet spectrogram, or whatever, frequency data, all the way around to the end here. All right, hope that's helpful and happy flying.